So now we come to the second part of our lecture, the part about t-tests. It contains the following topics. First of all, a few general discussions, one on hypothesis tests in general, the 8 steps, the 2 methods, rejection region and p-value. Then we will see how t-tests are specific cases of hypothesis tests, and that we see especially in the first 3 steps, linked to again the 4 elements of t-procedures. Then we will see how to do a t-test for a 1 sample example, and we will then use the rejection region method for the example on tall students. Then we will discuss the sheep example again with t-tests. We will look at the p-value method. We will look at the use of a computer output, one-sided versus two-sided alternative, and the case of unequal variances. Finally, we have a short example again of the paired data t-test. And finally, you will find homework and some ideas about how to go about preparing for the computer practical on the 2nd day of this course. The learning goals for the t-test. There are 2. One is to know how to specify the general pattern of a t-test, that is the first 3 steps, and then apply this pattern to a specific problem. In other words, know how to write the t-test. Well, to know the general pattern of a t-test, you have to know the 8 steps of a t-test, of a test in general, I mean, and secondly, the 4 elements of t-procedures. If you apply this to a specific problem, then you have to know which situation applies, and based on that, you will also know which are the 4 elements of the t-procedure that you have to use for that specific case. Well, then if you do a test, you have to decide on which method you use. Yeah, sometimes students use both methods, but you should always choose one, the rejection region method or the p-value method. And a specific problem can have a one-sided alternative hypothesis or a two-sided alternative hypothesis. Yeah, so this is a kind of overview of everything that relates to the t-test. Well, the general form of any test consists in our book of 8 steps. Yeah, of course, you can take certain steps together and then you would have 7 or 6 or 5. Yeah, the book does it a bit different altogether. It does not really write all these steps. The core of a test always is step 1, 2, 3. That is the null hypothesis and alternative. What is the test statistic and what is the distribution of the test statistic in case the null hypothesis would be correct. Well, how does a hypothesis test go? How does it work? Well, we always start with a null hypothesis and an alternative hypothesis. Yeah, usually the alternative hypothesis is the research hypothesis. It's the thing that you would like to know. And suppose in the first example, I would like to show that the mean body height of male Wageningen students now is different from what it used to be. Yeah, then that would be my alternative hypothesis, and the null hypothesis then automatically is that there is no difference. In other words, the mean mu is 180. Yeah, so in the null hypothesis, there's always an is equal to, as we will see later. The null hypothesis and the alternative hypothesis are about the population. So we start with a question about the population. Then we start collecting data and do, let's say, calculations, follow a certain procedure to arrive at a conclusion. And the conclusion, finally, is also about the population. So we say the null hypothesis is or is not rejected. That means the alternative is or is not accepted or proven or shown. And then in words we could finally say it is or it is not shown that, and then follows the alternative hypothesis in words. So in our first case, we could either conclude it is shown that the mean body height of male Wageningen student is 180, or it is not shown that it is different from 180, or it is not shown that it is different from 180. So always use the alternative hypothesis in words in your final conclusion. So that is step 1 and step 8, and in between comes what leads to the conclusion. First, the definition of the test statistic. It's the thing that we calculate from the data, and somehow it should be a good yardstick, or whether we can trust the null hypothesis or not. Secondly, we have to know how the test statistic behaves if the null hypothesis were true. And the technical term then is the distribution of the test statistic if the null hypothesis is true. And in our t-test, we will see then a t-distribution. Fourthly is the behavior of the test statistic expected under the alternative hypothesis, and that is a qualitative statement. It's not very exact, but we expect larger values, we expect smaller values than under the null hypothesis, or larger or smaller. And that depends on the alternative hypothesis and also on the type of test statistic. Well, based on step 4, we conclude that we should use a right-sided rejection region, a left-sided rejection region, or a two-sided rejection region. And we have to specify that rejection region for the given alpha. In a moment we'll see an example of this. Then we start looking at the data. So it's important also to remember that steps 1, 2, 3, 4, 5, they can be done before we have collected the data. So step 6 uses the data, and then based on the data we can calculate the test statistic. And 7, we wonder, is the outcome in the rejection region? In other words, do we reject the null hypothesis or not? And the rejection region also goes under the name of critical region. Well, if the answer is yes, then the null hypothesis is rejected. And if it's not, if the test outcome of the test statistic is not in the rejection region, then the null hypothesis still stands. It's not rejected. That does not mean that we think it's true or so, but just that we say it might be true. This is using the rejection region. Well, when we use the p-value method, we have slightly different steps. In step 5 and 7. In step 5, we only have to specify the type of p-value. We don't have to look up a critical region and specify a rejection region. So that is the advantage of a p-value. So when we have computer output, we usually prefer to use the p-value method. And finally, step 7. We do not look at the outcome so much of the test statistic, but at its relevant p-value. But that, of course, is determined by the outcome. And is the p-value smaller than alpha, then we reject the null hypothesis. Smaller or equal it should actually be. So these are the 8 steps. And we will now quickly go to the t-test to make this a bit more specific. Note that there are also some videos, some knowledge clips that can help you to go into more detail for certain aspects of the test. We saw the 8 steps, and the first 3 are specific when we have a t-test. Yeah? As I mentioned, in statistical tests, the first 3 steps form the core of the test. They sort of give a foundation, and based on that core, it's easy to find out whether or not you should reject the null hypothesis or not. Yeah, the t-test is a hypothesis test in which the test statistic has a t-distribution if the null hypothesis is true. And the first 3 steps of any t-test use the 4 elements mentioned before. Yeah, when we write a test, we have to specify these. So the first step becomes null hypothesis parameter is equal to something, some number. And the alternative hypothesis is the parameter is larger than or smaller than or is not equal to that specific number. Then step 2 of the t-test is always, we define the test statistic as t is equal to the estimator minus the null hypothesis value of the parameter. So it's the 3 dots that we see here. The 3 dots that come here in the null hypothesis parameter value. And the difference here is divided by the standard error of the estimator. Yeah, so parameter is the first element, estimator the second element, and the third and the fourth element are standard error and df. And that comes in step 3. Under the null hypothesis, t follows a t distribution with df, degrees of freedom, and df depending then on the situation. Yeah, the standard error is the formula for how we calculate the standard error from the data. And in the t, we specify the null hypothesis parameter value. And we may, if there is an n or so, or n1 and n2, we also specify those. But the results of t are not mentioned here yet. Yeah, that comes under step 6. Yeah, in steps 2 and 3, estimator and standard error are given in symbols. The null hypothesis parameter value and df are given as a number, so that must be specific. Now let's apply this to example A, the t-test. Here we see again the first 3 steps of the t-test, and now we have example A. The question, does mean body height of male Wageningen students differ from 180? Yeah, that is the alternative hypothesis. And we will use the rejection region method with alpha is 5%. Step 1, null hypothesis. Parameter is, well, the parameter in our case was the mean body height of male Wageningen students, mu. So we get here, mu is 180. The alternative hypothesis, mu is not equal to 180. Yeah, it differs from 180. Step 2, definition of the test statistic. T is estimator. Well, in the one sample situation, the estimator was y bar. Parameter mu, estimator y bar, standard error s over square root n, degrees of freedom n minus 1. Yeah, so we write y bar minus 180 divided by s over square root 25. Step 3. Under the null hypothesis, t follows a t24 distribution. Yeah, so you see it requires really little writing. Yeah, I tried to show you how you write a t-test briefly but completely. Brief but complete, that is the idea in writing the test. Step 4, under HA, t tends to. Well, under HA, mu is not 180, so it could, for example, be 170. If TS is 170, then y bar, or sorry, if mu is 170, then y bar will also be close to 170. So T will be negative. However, if mu is 190, then y bar will be close to 190 and t will be very positive. So t tends either to larger values or to smaller values. So please don't say it tends to larger and smaller values, but it's either or. So we use a two-sided rejection region because here we see larger or smaller. And we reject the null hypothesis if t is much larger than the t than what you would expect under the null hypothesis. So if it's larger than 2.064, or if t is smaller or equal than minus 2.064. And this critical value comes from table 2, but we could also find it in PQRS. Then, the outcome of the test statistic. Yeah, we can now use the data. Well, y bar was 184, so we get 184 minus 180. The standard deviation of y was 9. The 25 was already given. Well, and if we do the calculation, it's 4 divided by 9 divided by 5. 4 divided by 1.8 is 2.22. 2.22 is in the rejection region, so we reject the null hypothesis. And so the conclusion, null hypothesis is rejected, HA is accepted or proven. It is shown at alpha is 5% that mean body height in the population of all male Wageningen students is not equal to 180. Yeah, that concludes this test. Yeah, and again, this is brief but complete. It contains everything that we need, but we could also not leave things out. Yeah, only if we would use the p-value method, we might do it a little bit shorter because we don't have to find this critical value. So, how was this first t-test? If you found it very easy because you did this before, then I would say congratulations, keep it up. Yeah, try to make the t-tests for examples B and C before we show them on the screen. That would also be a good advice to those who found this difficult. Yeah, on the one hand, you are supposed to know all this. On the other hand, yeah, I'm now going to explain the t-test for the two samples case at a much slower pace. I'm going to explain every step in a little bit more detail. So let's go for the second t-test, namely the t-test concerning the sheep example. Yeah, the sequence of steps is still the same. Yeah, if you don't know these steps, it's worthwhile to learn them by heart so that you always know, okay, this is what a test looks like. Okay, step 1, the alternative hypothesis and the null hypothesis. Yeah, we want to compare the population means mu1 and mu2 for the new drug and the no treatment case. Yeah, and we can therefore say the parameter of interest is mu1 minus mu2, as indicated in the overview for situation 3 a couple of slides back. Yeah, the parameter of interest is mu1 minus mu2, so that should come in the null hypothesis and alternative hypothesis. The research hypothesis is that mu1 is lower than mu2, so mu1 minus mu2 smaller than 0. That is the alternative. The null hypothesis is that there is no difference. Yeah, so a lot of talk about this. What you in the end have to write down as a first step is null hypothesis, mu1 minus mu2 is 0, alternative, mu1 minus mu2 is smaller than 0, where it should also be, where the mu1 and mu2 should be well defined. Yeah, if you have not told anyone what you mean by mu1 and mu2, then of course this statement has no meaning. Yeah, but we have done that already. Yeah, so at the end of the test, we will conclude either the null hypothesis is rejected and HA is accepted, where accepted is fairly strong. Yeah, we really consider it to be very likely true. We can't say it's not a mathematical proof, but certainly in some cases the data speak very strongly in favor of the alternative hypothesis. So that's why we also sometimes say the alternative hypothesis is proven or shown, or words like that. Yeah, here we will mostly use accepted. Yeah, null hypothesis, that is one case, the null hypothesis is rejected. The other case is the null hypothesis is not rejected. And in that case, the HA is not accepted. In the second case, the null hypothesis still stands as a possibility. Yeah, so we did not prove it or so, but it's one of the options that is still open. Note that we never show or accept the null hypothesis, and we also never reject the alternative hypothesis. Yeah, so it's an asymmetrical relationship between the null hypothesis and the alternative. Before carrying out the test, we need to decide on alpha, that is the probability to reject the null hypothesis or accept HA, when in reality the null hypothesis is true. Yeah, sometimes that is possible. In reality there is no difference, but seemingly in the two samples there is a big difference. We choose usually alpha at 5%, as we do here. The definition of the test statistic. Well, the general rule is T is estimator minus null hypothesis value divided by standard error, so we will see how that works out. Yeah? What does a test statistic do? Well, it is a measure by which we sort of can judge whether we should accept or not, or whether we should reject the null hypothesis or not. Yeah, so it measures how well or how poorly the data match with the null hypothesis. Yeah, so in the case of the body height, for example, you would typically look at the sample mean, y bar. You compare that to 180. Yeah, we also saw that in the test statistic. Yeah, so if the difference is large, then you would say, oh, the null hypothesis is not true. If the difference is small, well, then you say the null hypothesis might be correct. Yeah, so that's what the test statistic does. It measures how well the data match with the null hypothesis. The general principle is applied here to the two sample case. So we write test statistic, T is estimator. Well, in this case, that's y bar 1 minus y bar 2. The null hypothesis value is 0. And the standard error, yeah, we can make that a little bit more specific. Standard error of y bar 1 minus y bar 2. So we could write the test statistic T is y bar 1 minus y bar 2 minus 0 divided by SP over SP times square root 1 over n1 plus 1 over n2. Yeah, and SP again, the pooled variance, SP squared, the pooled variance estimate. Yeah, we already calculated that before, and SP was 14.11 if I remember correctly. Yeah, note that in step 2, the test statistic is only defined with a formula. It's not yet calculated. So at this stage, we prepare a decision rule. Yeah, and intuitively the rule should be for very negative T, the null hypothesis must be rejected. So if y bar 1 is much smaller than y bar 2, then there is clear evidence that the alternative hypothesis is true. And only in that case. Yeah, so we want very negative T for rejection of the null hypothesis. Step 3, the distribution of the test statistic under the null hypothesis. Well, step 3 specifies what we can expect for T if the null hypothesis is true. Yeah, and roughly speaking, the answer is values between -2 and +2 are to be expected under the null hypothesis. Yeah, and William Gosset derived the distribution of t under the null hypothesis exactly. And we use it to determine the rejection region or p-value. Yeah, so the idea is, okay, we have this null hypothesis, we have a test statistic, and when it's between -2 and +2, or maybe -1.5 and +1.5, then we say, well, the null hypothesis could well be true. But if we in this case find -3 or -6, then we know, oh, this could not happen under the null hypothesis, so we must reject it. Well, in this case we write the null hypothesis, under the null hypothesis t has a t22 distribution. Yeah, the degrees of freedom come from the df in our formula, and for the case of 2 independent samples, the degrees of freedom is n1 minus 1 plus n2 minus 1, or n1 plus n2 minus 2. So that's 22 in this case. Yeah, so what we write is very simple. Under the null hypothesis, t follows a t22 distribution, but there is quite a world behind this statement. Yeah, and what you should remember also is that it defines what we can expect if the null hypothesis would be correct. And if we know what to expect under the null hypothesis, then we can also see in the result whether that is true or not. And if it's far off, then we know, oh, the null hypothesis was apparently wrong. Yeah, so here we see the form of a t-distribution. It's a symmetric distribution. The mean value is 0. It's a continuous distribution, and the +2 and -2 are somewhere on the edges. Yeah, note that this -2 is not exactly at the point where alpha is cut off, but it's just a general value near the edge of the distribution on both sides. Yeah, so we see the rejection region. That's the green part in on the x-axis, on the t-axis actually. So we say if we cut off here alpha of the distribution, the total area under the curve is 1, and we cut off alpha, and then at this point, this is where the rejection region starts and goes further to the left. Yeah, so these values favor the alternative hypothesis. So in step 4, yeah, we say, well, under HA, t tends to have smaller values, yeah, because in that case, y bar 1 will be small, mu1 is smaller than mu2, so y bar 1 will also be smaller than y bar 2, so t will tend to have negative values. Yeah, so we reject the null hypothesis when the outcome of the test statistic is very small. Yeah, so under step 4 we write under HA, t tends to have smaller values, so we use a left-sided rejection region or a left-tailed p-value. Well, this latter part could also be part of step 5 actually. Okay, then the question is, what is exactly that area? To specify the rejection region, we have to find a critical value from table 2. Here it's negative, so it's t22 0.05 and then with a minus sign, and the t22 0.05 is 1.717. Yeah, so in PQRS we can see this more clearly. We have a t distribution with 22 degrees of freedom. On the left-hand side, we cut off 5%, and then we see here the critical value minus 1.717. Yeah, so how to do that? We choose a t-distribution, we choose degrees of freedom 22, fill in 0.05 and read the critical value here. Rejection region, all outcomes of t smaller than or equal to minus 1.717. So we write rejection region t smaller equal minus t22 0.05 is minus 1.717. Yeah, that is the step 5. So now we have come to a decision rule because we know what to do in each for each outcome of t. If it's smaller than this, we reject the null hypothesis, and otherwise we don't. Now we can look at the outcome of the test statistic, and for that we can use the R output, computer output in general. Yeah, so we could calculate the outcome of t by hand as follows. Here we have the mean for control and we have the mean for treated. So this is the group 1, actually the drug, and this is the non-treated. We see the mean and the standard deviation for each of the two. And then we could calculate t by hand. Well, we found y1 is, the values are given here. The SP is 14.1, and so we could calculate t as minus 2.27. Yeah, but R can do that much quicker than we do. If you use a command that looks a bit like this, or maybe exactly like this, t-test treated versus control, the alternative is less, so the treated has lower values than the control. We assume equal variances, then we get to see a two-sample t-test. T is minus 2.27, df is 22, and that's it. Yeah, so because in this case we are only interested to know the outcome of the test statistic. So we write in step 6, t is minus 2.27. Yeah, and if you have computer output, you don't have to write more, you don't have to do these calculations, because that's what we use R for. T is minus 2.27. Now, step 7, 8. T is minus 0.27. This is definitely smaller than minus 1.72. So T is in the rejection region. The null hypothesis is rejected, HA is accepted. It is shown that sheep treated with the new drug have, on average, fewer worms after 6 months than non-treated sheep. The conclusion finishes the circle. Yeah, we started with a research hypothesis expressed in the parameter, and we now draw a conclusion about this parameter. Yeah, note that again, that if the outcome of T had not been in the rejection region, the conclusion would have been the null hypothesis is not rejected, HA is not accepted. It is not shown that sheep treated with the new drug have, on average, fewer worms than non-treated sheep. Yeah, so this is a kind of pitfall for some students who would like to write. It is shown that the treatment gives the same number of worms on average as the non-treated case, and that is not true. We did not show that. Yeah, also not in this under this last assumption. Yeah, so we have seen the two ways in which you could correctly specify the conclusion. Now the first variant, that is the t-test using the p-value method. What is the p-value in a test? The p-value is the probability under the null hypothesis, and so we assume the distribution that we have used under the null hypothesis, in this case the t22 distribution. It's the probability that the outcome of the test statistic is more extreme than the one observed. Well, in this case, more extreme, more supportive of the alternative hypothesis means more negative. So the p-value that we use here is the left-tailed p-value. So here it is defined as the probability under the null hypothesis that t is less than or equal than the outcome, which was minus 2.272. And if we plug that value in here in PQRS, so we choose t distribution, 22 degrees of freedom, and then minus 2.272 here on the t-axis, then we find a left-tailed p-value of 0.0166 and a right-tailed p-value of 0.9834. Okay, this p-value is compared to 5%, so the alpha that we have chosen, p-value is less than 5%, so we reject the null hypothesis, etc. Yeah, alternative hypothesis is accepted, and so on. And then the conclusion in words. Yeah, so that is the, if we would do the t-test using the p-value method. Whether you use the p-value method or the rejection region method, the conclusion should always be the same. But if we have computer output, yeah, then, or maybe PQRS at hand, then the p-value method is often easier. Yeah, so how would it work, the whole, all the steps with the p-value method? Well, we again have under step 4, under HA, t tends to smaller values. That means we reject the null hypothesis if the left-tailed p-value is less than 5% or equal to 5%. Outcome t does not change, minus 2.27. The LPV, as we saw, is 0.0167, and that is also given here in R. Yeah, the R output, we have a t-test, treated, control, alternative is less, var dot equal is true. The t is minus 2.27, and the p-value is 0.0167. So this means using the R output, we only have to compare this with 5%, and then we're done. Yeah, so we don't have to look up a table value. Yeah, LPV 0.0167, less than 5%. The null hypothesis is rejected, HA is accepted. It is shown that sheep treated with the new drug have, on average, fewer worms than non-treated sheep after 6 months. Yeah, so that is the complete story of the p-value method in this case. Well, in general, what do you see in the R output? If we look here, t-test, x is treated, y is control, alternative is less, var dot equal is true. We find outcome of the t of the test statistic, minus 2.27. We find the degrees of freedom, the relevant p-value, and this p-value is attached to this alternative, less. Also the sample estimates y bar 1 and y bar 2 are given. Yeah, so we see the outcome of t, we see the alternative hypothesis reflected in the R output, we assume equal variances, t22, and finally here the p-value. Yeah, what this shows is how we could, of course, if we had a different question, if we wanted to show that the treatment gives more worms, then we would have used greater instead of less, and then the p-value would have been 0.98. So then it would say that the data do not prove that the treated lambs have more worms, of course. Okay, so this is what our output looks like. Then, rejection region for a two-sided alternative. Suppose that we had mu1 minus mu2 is not equal to 0. Then we would still have the same distribution of t under the null hypothesis, but then we would say if mu1 minus mu2 is negative, then t would shift to the left. So this distribution would shift to the left. If mu1 minus mu2 is positive, the distribution shifts to the right. So we want to be defended against both cases, so we reject for very small and for strongly negative t and for strongly positive t. So we say reject when the outcome of the test statistic t is too large or too small. And the red and the green region have then to be found based on the table value in table 2 of Ott and Longenecker. Yeah, so for this particular case, we would reject the null hypothesis if t is either strongly negative, so less than minus t22 0.025. Yeah, all outcomes of t smaller than minus 2.074, as we can see here, this is the critical value, or values for t larger than plus 2.074. And if you want to write it in sort of in a very nice mathematical form, we reject for t inside this set minus infinity to minus 2.07 and or t in 2.074 to plus infinity. Yeah, so the rejection region is here and on this side. Yeah, so that is the rejection region for a two-sided alternative hypothesis. Then the p-value for a two-sided alternative hypothesis. Well, the p-value is the probability under the null hypothesis that t is minus 2.27 or more extreme in the direction of the alternative. Well, if we now have a two-sided alternative, then more extreme means either smaller than minus 2.27 or larger than plus 2.27. Yeah, and if you would then plug in this 2.27, we see here on the right side, the right tail p-value is 0.0166, and the left tail p-value was also 0.0166. So these two values together add up to 0.033, and that is automatically calculated in R if we give as an alternative two-sided, and still var.equal is true. Yeah, so we could find this 0.033 with R or using PQRS, but then we should add two extreme, two tail probabilities, the right tail probability and the left tail probability. Okay, then the case of unequal variances finally. If the variances are not equal, yeah, then we have a different standard error, at least in formula, but since the n1 and n2 are equal, n1 is 12 and n2 is 12, the outcome will still be exactly the same. So the standard error estimate changes, and other consequences are that the distribution of t is no longer exactly known. So we use a certain t distribution as an approximation, and the degrees of freedom are calculated from the standard deviations and the sample sizes in the two groups. But you don't need to know that formula, but you can find it in the book. Levene's test helps us to decide which case we should choose. Yeah, because since it is population variances, we don't know them. We can estimate them, but we do not know them. But using the sample variances, we can do the test, the Levene's test. Levene's test, Y versus group. Yeah, Y contains treated and control data, and we see here an F value and a P value. Well, we do not discuss how Levene test comes to a value. We only look at the tail probability 0.71. This is much larger than 5%, so there is no reason to reject the null hypothesis of equal variances. Yeah, so the null hypothesis is sigma 1 squared is sigma 2 squared. And if the p-value is very small, less than 5%, then there is clear evidence that this assumption is wrong. And in that case, we should use the unequal variances two samples t-test. Yeah, note again the formula for the standard error, which is slightly different. If we want to use the non-equal variance t-test, we can still use the R output. Yeah, the p-value is in this case almost exactly the same as before, but that is because the standard deviations were so similar. So yeah, but how do we do that? Well, we again ask for a t-test in R, t.test. X is treated, Y is control, same as before. Alternative is two-sided, let's say. And the var.equal is false now. No longer is true, but is false. And then we no longer get the two-sample t-test, but the Welch two-sample t-test is called. We get the same t is minus 2.27, degrees of freedom slightly different, and the p-value is again 0.033. So maybe only in the fourth decimal place or so it is different. So again, there is clear evidence, yeah, that there's a difference in mean number of worms between the two groups. Yeah, we also see here a confidence interval that is printed by the t-test. So this could also be used. And we saw a very similar confidence interval on a previous slide in the end of part 1. Yeah, that was also minus 25 and minus 1.1 as limits. Okay, this concludes to a large extent this lecture. Homework, yeah, make sure you know how t-procedures work. Yeah, this is really core. I have written in on page 10 or 12 or so in the study guide a small portion on how to study, and the t-procedures, yeah, is something that you are supposed to know already. So today I've given a review of this. Make sure you know this from beginning to end and backwards and forwards, so that yeah, you can really easily apply it, because in later situations when we do regression and analysis of variance, t-tests will still be an important part of the material. And then we can apply these general principles that we have learned today using the elements of the t-procedures. Review the slides of lecture 1. These slides, maybe review this lecture, but especially maybe the summary slides. Yeah, if I think of t-procedures, then the general principle of confidence interval, the general principle of t-test, and how to apply them for different elements. So know for each situation what the elements of the t-procedures are. Then it's worthwhile and important to be prepared for practical 1, computer practical 1, which is held on the first Tuesday of week 1. Read the R Commander manual, study guide. I must think now, I did not look it up, but I think it's about page 50 or 60 or so. R Commander manual. Download and install R and R Commander. Follow instructions on Brightspace. Download and unzip the data files from Brightspace and store them in a separate folder. If you are unfamiliar with R Commander, watch the R Commander clip on Brightspace and use the discussion platform to find a partner for the practicals. Yeah, it's very useful to work with someone else, not do everything on your own. Well, that brings us more or less to the end. I wish you lots of success with mastering the T procedures. Tomorrow in the computer practicals, you will have another opportunity to practice with them. So use that opportunity. Also in the pen and paper practicals, we will come back to these. So again, make sure you are present at these in these sessions. It's a very important basis for the rest of the course. Then for lecture 2 as a preparation, yeah, you could have a look at the body height exercise in the study guide, where you can look at 6 different ways to do a test, depending on what the alternative hypothesis is and what the method is, p-value or rejection region. Yeah, so just as an exercise to really get you going in the T procedures. The exercise is given on page 14. Read chapter 6 in Ott and Longenecker and maybe preview the slides of lecture 2. Well, one more case I would like to show, that is the paired t-test. For the case that we looked at, yeah, we had 16 patients with high blood pressure. We collected 16 observations on the differences of before and after treatment. Our null hypothesis is mu d is 0 versus mu d positive. Yeah, we expect that after treatment the blood pressure will go down. At least that's what we would like to test. And so we have as an alternative hypothesis mu d positive. Then test statistic t is estimator minus 0, estimator is d bar, divided by standard error, the SD over square root n. Under the null hypothesis, we use a t distribution with n minus 1 is 15 degrees of freedom. Under HA, t tends to larger values, so we use RPV. We find as an outcome of the test statistic, t is 6 divided by 12 over square root 16, which happens to be equal to 2. The right-tailed p-value in PQRS is 0.032. T distribution, 15 degrees of freedom. Outcome is 2. Then the RPV is 0.032. So the null hypothesis is rejected. HA is accepted. It is shown that the mean blood pressure of high blood pressure patients after 2 weeks of medication use goes down. Well, this then is the very last thing I'm going to say for this first lecture. Again, lots of success with preparing for tomorrow and day after tomorrow, and with digesting the material of today. See you again.